Good afternoon, everyone. Welcome to what I think is going to be the penultimate of these focus sessions for the Scottish Arctic Network series. It's been running over the last few weeks, and it's been organised by Glasgow Caledonian University, University of Aberdeen, and the University of the Highlands and Islands. Just a little reminder, we are recording this event, so the contributions, certainly by the speakers and by the attendees, will help inform any of the follow-up actions and discussions that we will have. So just by way of introduction, my name is Finlo Cottier. I'm based at the Scottish Association for Marine Science, and I'm also an adjunct at the Arctic University of Norway based in Tromsø. So the network series that has been brought together has been to allow people to come and share their interest in the Arctic across quite a wide swathe of disciplines. I've attended two previous events before this, the biodiversity session, the education session, and they all had the same aim, which was about communication and collaboration, but the discussions went in different directions. I'm sure that the discussion we'll have today will also carve its own path through the discussion points which have been put forward. It's worth remembering where this is come from, where it's based upon, and it's the sort of the policy framework, sort of bold and ambitious policy framework that the Scottish Government's launched in 2019. And this has really given us a strong mandate for our engagements with other Arctic nations and for projecting Scotland's contribution to the High North. And research into geophysics and coastal erosion is just one of those contributions that we can make, and we've been discussing those other contributions in previous network events as part of the series. I'm going to make a brief apology if I inadvertently shorten the title of this to just geophysical changes, and I happen to omit the eroding coastlines. It's not because I'm ignoring that part, because it's clearly wrapped up in geophysics, and it's actually important that we highlight it. And I'm just going to show you this table here. Interesting set of statistics. So the ocean, the Arctic Ocean is about 1% of the world ocean volume, but it contributes about 35% of the world coastline. So the coastal margin and the coastal communities are incredibly important there. We also see the contribution of river runoff. So about 10% of the world's river runoff comes into the Arctic as well. And we're going to hear more this afternoon about the freshwater components of the Arctic from both rivers and from glaciers. I think in terms of change, it's very often the geophysical changes that are immediately picked up by the media. I think most people would be aware that the Arctic sea ice is diminishing, the Greenland is melting, and probably also that the Arctic has been experiencing heat waves. But there's many other aspects of geophysical change that are just as important and perhaps a little bit more subtle. And one of those is thawing permafrost, and that's something we'll hear about this afternoon, and also changes to the ocean. And again, I think we'll be hearing more about that this afternoon as well. And the ocean is perhaps one of the more important geophysical connections that binds Scotland to the Arctic, with change and evolution of that on many timescales. One of the aims of this networking series is to tackle fragmentation of Scottish Arctic research, but I think actually for geophysics, we're in quite a good position. We've benefited from, through the Scottish Funding Council, with research pools, the Marine Alliance for Science and Technology Scotland, MASTS, and the Scottish Alliance for Geoscience, Environment and Society, SAGES, and we'll certainly hear more about those this afternoon as well. And so these communities provide a good level of coordination and communication between researchers. So I think this idea of fragmentation is perhaps less prevalent in the geosciences. So I'll finish there, and it's a great pleasure to introduce today's speakers, a really superb lineup of expertise in geophysics and coastal processes. So first, we're going to have Mark Innell, who's the director of SAGES, and I'm sure he'll talk us through the Scottish geoscience community and perhaps discuss some of the oceanic connectivity with the Arctic as well. Tom Cowton from St Andrews University, who will focus on Greenland melt. Robin Turena from the Scottish Association for Marine Science, who will consider the importance of permafrost and the geochemical properties of Arctic rivers. And then finishing up with Ian Kelman, a thematic lead on natural hazards for the University of the Arctic, who will talk more about Arctic coastal erosion. We finished the afternoon with a group discussion and some concluding remarks. So I'm going to stop there. I'm going to stop sharing my screen and pass over to Mark Innell.
Thanks, Finlo. So I will just share my screen. So is that sharing okay? Are you seeing the right view is my question.
It's good.
Yep, great. Okay. Yeah, so it's Finlo. So thanks for the introduction, Finlo. Yeah, my name's Mark Innell. I'm the director of SAGES, which is one of the alliances of network pools of research expertise in Scotland. And I'm going to talk about some of the networks that are available to researchers, Arctic researchers in Scotland, a little bit about the history of this document that Finlo has already alluded to, the Scotland's Arctic Policy Framework. And then I'll talk a little bit about the oceanic science, the connection between the Atlantic Ocean and the Arctic, and hopefully give a nice segue into Tom's stuff about ice sheets and fjords. Okay, and the logos here on the right-hand side, the Arctic Circle, the Arctic Office, the UK Arctic Office, SAGES and MAST. Those are the networks I'm going to talk a little bit about. And hopefully everyone is reasonably familiar with this document, or at least knows of its existence, which was published by ScotGov in 2019, September 2019. Okay, so this really all started in 2016 when the First Minister was invited to share the floor at the Arctic Circle with a keynote presentation, the Arctic Circle Assembly in Reykjavik. And the Arctic Circle is a truly international alliance of nation states, Arctic nation states, but there is a real connection with Scotland. There are many geopolitical similarities between rural Scotland and often the subnational issues that the member states, the Arctic states, you know, we're talking big countries, USA, Russia, Canada. Arctic isn't their whole country. So there are a lot of Arctic issues which have a lot of resonance with Scotland, particularly, as I say, the rural communities, ecotourism, the new trade routes, and challenging geoscience environments. And after the First Minister's presentation, she shared the floor with John Kerry, who's now President Biden's climate envoy. So it really is a political collective with clout, the Arctic Circle. And when First Minister returned, she mandated Fiona Hislop, who Cabinet Secretary for Culture, Tourism and External Affairs, to work up Scotland's policy framework for the Arctic. There followed then this meeting in Edinburgh in 2017, a forum, one of the Arctic Circle Forum meetings, where SAGES was participating and helped organise that. We also fed into the consultation exercise, which was led by Glasgow Caledonian University and the UHI, the ERI, the Environmental Research Unit in Thurso, did the scoping study. And then the policy framework was developed and, as Finlo says, published in 2019. And the kind of developments since then, leading from these high-level interests in the Arctic issues with Scottish Government. This year, the Scottish Government has been offered a seat on the Arctic Circle Advisory Board. And previously, UK representation had been very much, I mean, there was the UK Arctic Office, but more southern focused, shall we say. So that's a very welcome development. If we turn now to the networks, the Scottish Funding Council in Scotland funds what are called research pools. These are across the higher education institutes in Scotland, and the two, as Finlo said, most relevant to Arctic geoscience, I would say, are SAGES, which I lead, and MAST, which David Paston at the University of St Andrews leads. And within those themes, visit the websites. The two areas in SAGES most relevant to the Arctic are the theme that Finlo and Sean lead on the atmosphere, oceans, and climate. And also there's a forum on ice ocean research development that Tom Cowton leads. Within MASTS, it's a slightly different organizational structure, but I think the two thematic areas which have most Arctic interest in MASTS are the marine climate change theme led by B. Burks at Marine Scotland, and the technology platforms and sensors led by Lars Boomer at St Andrews, I think, or that may have changed. So these networks are not exclusive clubs. They are membership organizations, but members they're welcome to have associate memberships, but as members are welcome to join. There's a very much an open door policy to join in with these initiatives. And only last year, I just give you this example of the annual science meeting of MASTS, a special section on the changing Arctic Ocean, and the annual science meeting that SAGES ran with keynotes from Francesco Bertoldi, who's the Scottish Government Civil Service lead on the Arctic matters, and Finlo is involved there as well, and a special session on the fjords, which Tom led. Okay, I'll switch gears slightly now, moving to the connections that Finlo alluded to between the Arctic and the Atlantic. Scotland is very much an Atlantic nation. People may not be familiar with this kind of map, but these red arrows are warm ocean currents taking warm water to the Arctic. And there's evidence in very recent papers that the Arctic Ocean has been warming, and the heat transport, so the heat delivered by the warm Atlantic into the Arctic, has very much increased over this last 20 to 30 year period. There are some large-scale international programs which Scottish researchers are involved in, trying to measure these pathways of warm water entering the Arctic and cold water leaving the Arctic and fresh water leaving the Arctic. And Scottish researchers are very much at the forefront of this. Okay, I'm now going to finish off trying to see if this will work. This is just to remind us that we do field work. We used to do field work, and we will do field work again. So I'm just going to take you through a story from Scotland up to the Arctic, from the ocean and into the fjordic environments, which hopefully gives a nice segue for Tom. Let's see how we do. Is that showing on people's screens? Is it moving? Yeah. Okay, this is a story really of the use of these devices, underwater robotic gliders, which we're able to deploy from a small boat on the west coast of Scotland, and they make their way all the way into the Arctic Ocean. So these are small instruments, they're only a couple of meters long, fully autonomous, and what you see here is an animated simulation of this instrument making its way to Iceland from the west coast of Scotland. It's a simulated animation, but the data you see coming out the tail is real, in the sense that it's the real observed temperature of this glider as it flies. The warm colors indicating warm water, and you see as we dive down into the abyss over the continental shelf and into the deep ocean, we drop down into these colder waters. And now we speed it up, and you see the passage over several months of this glider winding around, being moved around by the ocean currents. But there you see the very cold water at depth and the very warm water at the surface, and sub-zero waters. We're down into sub-zero Arctic origin waters leaving the Arctic Ocean. We now move over to Greenland, and this is the work I think that Tom will talk more about. Here's a picture of a fjord in Greenland. The warm arrows are warm Atlantic water coming in, and all the way on this left-hand side interacting with the ice sheet. So warm water's coming in at depth, melting the ice, leaving the fjord at the surface. So a very exchange process of oceanic water melting these ice sheets. We'll now jump our way over to Svalbard. And I mentioned here the Changing Arctic Ocean program, which is a £16 million program that the UK researched. I'm going to hand over to Sam Black now to give you a 30-second clip. Okay, so that was my final slide. Just on the last slide here, I put up the networks that I talked about that we can become involved with. The last one, the University of the Arctic, Finlo had up at the front there. And that was a student, that was an undergraduate student giving the little YouTube clip at the end, who'd done a study for a degree in marine science with Arctic studies in Scotland, offered by the UHI. So very much part of the educational availability as well in terms of networks in Scotland. The other one I put up that I didn't mention is the International Arctic Science Committee, and I wonder if that might be something we discuss during our discussion session. Okay, I'll stop there. I realise I've a minute over, Finlo, sorry, but I will stop there. Thank you.
Yeah, thanks, Mark. We just didn't quite catch Sam, or I didn't catch Sam on the clip. If there's a link to that, you can put in the chat. That would be fantastic, because he's got good messages, Sam. So we're going to jump straight to Tom just now, and Mark will sort of set you up quite nicely, Tom. So over to you.
Great, thanks, Finlo, and thanks, Mark. Let me just get the screen up. Hopefully this will work. Is that the right screen coming through now? Yeah, brilliant. Okay, fantastic. So thanks, intro, and yeah, thank you, Mark, for that, and that wonderful animation at the end. So nothing quite as snazzy in this presentation, I'm afraid, but here we go. So my name's Tom Cowton, and as billed, we're moving on now to look at the Greenland ice sheet in particular. So the Greenland ice sheet in a changing climate. So what I want to do here, obviously 8 minutes isn't terribly long, but give a very, very brief overview of the Greenland ice sheet and why it matters to us, and then focus in a little detail on just a few snapshots of research going on in Scotland. And I'm afraid this does have a bit of a St Andrews bias, but I will flag up some of the networks as well. So the Greenland ice sheet, here it is. I imagine that, let's get the laser pointer on.
Tom, we're just in presenter mode here, is what we're seeing.
Okay, so let me see if I can fix that. Sorry about that.
Anything.
You should have a button that says switch screens up on the top bar somewhere. You should just be able to switch them.
Remote control, add more. Oh dear. Never mind. Maybe I'll just show you it in presenter mode rather than wasting the 8 minutes I have. So let me just escape from this. Okay, so can you see the screen okay if I just leave it like that? Is that, there we go.
Can't see anything just now, Tom. Don't worry too much about the time. We'll
okay.
Take a moment.
That. I'll tell you what I'll do. I'll just share my. One more go at this. Share screen.
That's looking good.
Okay, so you see the proper slide now. Yeah. Okay, right then. Sorry about that.
Starts from now, Tom. So
okay, thank you. That's bought me 30 seconds. Where were we then? Okay, so Greenland. Yeah, so you probably recognise Greenland. It's the largest body of ice outside of Antarctica. It's made of glacial ice, so that's effectively compressed snow, so not to be confused with the sea ice, which covers the Arctic Ocean. It's absolutely vast, so it's 1.7 million kilometres squared or thereabouts, and over 3 kilometres thick in parts. So it's a huge body of ice, and that's enough to raise sea levels by about 7 meters if it was to melt completely. So clearly it's a very significant object on a global scale. We're particularly interested in it at the moment because it is obviously vulnerable to climate change. And it's more vulnerable to atmospheric warming than the Antarctic ice sheet, simply because Greenland is that bit warmer than Antarctica is, which is an extremely cold environment. And it's been experiencing mass loss in recent decades, and this has accelerated significantly. So if we look at the figure on the right, on the left, and follow the purple line here from 1970 onwards, this shows the sort of cumulative sea level rise. It was melting sort of steadily until about 2000, and then that really accelerated from 2000 onwards. And it's contributed about 15 millimeters to sea level rise since the year 1970. And this mass loss hasn't been uniform. It's been concentrated particularly around these fast-flowing outlet glaciers, which drain down from the ice sheet into the ocean. And that's a theme I'm going to touch on a couple of times in this talk. We're interested in the ice sheet because we expect it to be one of the biggest contributors, if not the biggest contributor, to sea level rise in the 21st century. This figure here shows some of the most recent projections of how the ice sheet is expected to do this over the next 100 years. So you follow the red line here, that's the projected sea level contribution from Greenland under the RCP 8.5 scenario, blue line for RCP 2.6. And you can see that sort of ramping up to contribute about 100 millimeters to sea level by the end of this century, so a really significant amount. It's worth noting, though, also the size of these shaded areas, so the error margins on this are very large, and that's one of the reasons why it's such a focus on research, is because it's still, there's a lot of uncertainty in trying to predict how the ice sheet is changing and will continue to change. And this is particularly due to the response to those outlet glaciers, which are a bit complicated. So to focus in on St. Andrews as a sort of example of research into the Greenland ice sheet from a sort of Scotland perspective, we have a glaciology research group of 15 staff and research students. There are two components to this. So a lot of the research we do is into ice sheet change, that's Greenland and Antarctica. We also look at Himalayan glaciers, won't focus on that today. And the ice sheet research that we conduct is focused on processes that occur where the ice sheet meets the ocean. And so I just want to talk through three brief examples of that here. So as I mentioned, these outlet glaciers, so you can see example here, this glacier, this is from a satellite image flowing down into a fjord here, and these are experiencing this rapid thinning and retreat. But it's actually really quite hard to isolate the processes going on here, and that's because this is this interface between the ice sheet, the ocean, and also obviously the atmosphere above, and that makes these connections quite complicated. So one of the bits of work that we've led on in conjunction with other researchers at Scottish institutes is using remote sensing to track the retreat of some of these glaciers. All the squiggly lines in this image here is the terminus of the glacier at one point in time. And by doing that, we can not only sort of keep an eye on how rapidly these glaciers are retreating, but we can also try and sort of pin down exactly what environmental forcings it is that are triggering these glaciers to retreat. So whether that's in the atmosphere, the ocean, or both. Something that we looked at in a lot of detail in St. Andrews is iceberg carving. So this is the process by which icebergs break off these glaciers and into the ocean. And this is a huge source of mass loss. So about half the mass from Greenland that's lost each year occurs into the oceans in this manner. But it's also really hard to represent in ice sheet models. And the challenge is that these things are so small, the processes are so fine scale that it's very hard to put that into a continental scale model. So one of the big projects that we've had recently, a NERC-funded project that was looking at this challenge specifically on how we represent this in ice sheet models. And the process really was to use very high resolution models to sort of constrain these processes better, and then find ways of upscaling that into the continental scale models that we use for these sea level rise projections. And then final example, fjord processes, as Mark showed that wonderful animation of at the end. So we're interested in the fjords because they form this gateway between the ice sheet up here and the ocean down here. And in particular, it's the circulation in these fjords that allows that warm water that's circulating in the oceans to make its way up to the ice sheet and actually affect these outlet glaciers. And so one of the processes that we've been interested in studying is this circulation, and using numerical ocean models to examine what really controls the strength of that circulation. And you can see this graphic here showing the flow of water at depth, as Mark illustrated, up towards these glaciers where it's causing melting. So by using these models, we can try and constrain essentially how strong the circulation is and whether that will change over time as well. So all the research I've mentioned with the sort of St. Andrews lead has been numerical modeling and remote sensing. That's kind of what we've been doing lately, but I did just want to flag up that other researchers in Scotland are active in fieldwork in Greenland. We're not all just staying at home. People are going out there, or at least they were until COVID. So from SAMS, Edinburgh, Aberdeen, I know there are people there who have been undertaking significant fieldwork in recent years. Anyway, finally, Mark's already covered this, which is great, but just to touch on this, we have these networks in Scotland that enable us to collaborate between institutes. And on this topic, this Forum for Ice Ocean Research Development, or FJORD, is really the key network for bringing together researchers into these topics. And there's over 50 full-time staff and research students part of this network. And we have various activities, and this can include encouraging collaborative research and funding bids. So particularly in 2019, we were successful in proposing a NERC highlight topic on Greenland marine terminating glaciers. And also trying to increase the visibility of Scotland-based research and expand those networks internationally. So for example, we hosted a session at the EGU General Assembly in Vienna in 2019. So, okay, apologies for the disruption at first, and that was given a bit in haste, but anyway, thank you for listening.
Thanks, Tom. That was great. Really showing the excellence in glaciological research in Scotland. Some great examples and some examples of how we connect and network together as well. So many thanks for that, Tom. We'll switch over to Robin just now. If you're ready to go, I'd like to share your screen, Robin, and the stage is yours.
Okie dokie, thanks Finlay. 1 second. Okay, can everyone see my screen okay?
That looks great, Robin. Thank you.
Great, okay. Hi everyone. So yeah, I'm changing tack again now with this talk. So instead, we're going to be talking a bit more about permafrost degradation and nitrogen cycling processes in Arctic rivers. So the work I'm going to talk about is quite a nice overview of the impacts of permafrost degradation and, taking these ideas to the Arctic marine environment. So I'm going to be talking about some work that was really the hard work of a master's student at the University of Edinburgh, and really his brainchild, really. Okay, so just a bit of an overview. Finlay mentioned this at the start. So the Arctic is a very unique ocean. It only contains about 1.3% of the global ocean volume, but it receives around 10% of the total global riverine discharge. So what that means is the export from these rivers has a large anything that's being exported from these rivers has large implications on the coastal marine environment. The Arctic as a whole has very extensive areas of permafrost. So when we look at these different river catchments here, so we have the Mackenzie, the Yukon, the Kolyma, the Lena, the Yenisei and the Ob. Around 80% of their catchment area is covered by permafrost. And these Arctic rivers, these 6 major Arctic rivers are covered by the Arctic GRO program. So this is a biogeochemical sampling program where they take samples both seasonally and interannually of all of these rivers to look at the changing effects of the biogeochemistry, not just the seasonal flow, but also what's happening over time. So obviously, as we're warming the Arctic environment, then this is leading to permafrost degradation. So this work was really trying to understand the importance of permafrost degradation in terms of the biogeochemistry of the nutrient nitrogen. So nitrogen is particularly important because in the Arctic Ocean, so in the marine environment, it's the primary limiting nutrient to phytoplankton. So if we have an increased export of nitrogen as a result of permafrost degradation, then this may have impacts on primary production in the coastal marine environment. Okay, so this work as part of Adam's thesis was looking at whether there is an increased nitrogen supply, so dissolved nitrogen supply into Arctic rivers as a result of permafrost degradation. So this was looking at the signatures in at the river mouths of these 6 major Arctic rivers, but also looking at an in-depth transect through the Kolyma River. So this is showing the Kolyma River from an area of permafrost thaw into a permafrost influence zone, and then out into the riverine and estuarine zone. So within these 2 kind of areas of method of research, so an in-depth look at the Kolyma and an overview of the seasonal cycling of these different rivers, he measured the concentrations of nitrate and dissolved organic nitrogen. So these are the 2 key forms of nitrogen that we see in rivers, and also their isotopic signatures. So this is just a very brief overview of the findings of this work, but essentially from looking at the Kolyma River in detail, what he found was that the permafrost degradation was leading to really high amounts of organic nitrogen being released from the soil and the ice. and that there was a rapid nitrification of that organic nitrogen into the form of nitrate. And this nitrate was what was being observed further downstream through the Kolyma River. So as we went into the riverine zone. Interestingly, the other important finding was that due to anaerobic conditions in the soil, there was some denitrification occurring, but that led to a unique isotopic signature in the nitrogen that was being exported from this permafrost thaw. So this was a useful signature from looking essentially at this detailed study for then taking that to look at the Arctic rivers. Okay, so now moving on to these 6 main Arctic rivers. So we had samples from the river mouths, essentially. So this is taking an integrated view of all of the processes that are happening throughout that Arctic catchment. Okay, so it's not just seeing nitrogen being exported from permafrost degradation, but also the DON that we'd expect to see in the fresh dissolved organic nitrogen in topsoil, so not as a result from permafrost degradation as well. This is quite a complicated plot, so all I really want you to get from this is if we look at this range and this yellow band here, this is what we'd expect to see without any influence of permafrost degradation. So these are kind of the natural values or the natural range that we'd expect to see. And as you can see, most of the rivers don't really show any elevation above this band, so not much of an influence of permafrost degradation at this time. Apart from the Ob River, which in particular in winter months you have this elevated 15N signature in this second plot here, but also you can see that there's a very high nitrate signature in these winter months as well. So the fact that we can see this signature at the mouth of the river is really, it's demonstrating that the integrated signature from the whole of that catchment is showing this permafrost thaw signature. But obviously it depends a lot on the flux of the river. And as you can see, the discharge in winter months is much smaller. So we're seeing this elevated signature because it's not being diluted by other natural processes. Okay, so this work kind of gives a nice overview of some of the ideas or the ways we can look at trying to understand permafrost degradation in the Arctic. And the results from the study really showed that at the moment, the majority of the nitrogen flux is still from the fresh DON in organic rich topsoil, so not from permafrost degradation, but that the Ob River is the river that seems to be most affected by permafrost degradation at the moment. And this is the river catchment out of all of the 6, which has the greatest extent of thaw zones. So there's discontinuous permafrost present under large peatlands in these areas. And there's also an important thaw mechanism called active layer deepening, which is happening in this river catchment. Okay, so just quickly for the implications for future work, hopefully this study kind of highlights the importance of large international collaborative and multi-year programs. So this work wouldn't have been able to happen without the Arctic GRO program and also the Changing Arctic Oceans program. So this collaboration is really important to start to look at these kind of large spatial and interannual studies. And the influence of permafrost degradation is likely to increase in the future. We're seeing increases in fluvial sediment load by erosion. The deepening of active layers is happening across all of the Arctic. And there are certain river catchments such as the Kolyma and the Lena rivers where they have extensive ice deposits. So they will be particularly susceptible to permafrost degradation in the future. So the signatures that we're seeing in the Ob River may become more widespread in other rivers in the future. Okay, and I'm just going to stop there.
Great, thanks, Robin. That was super. There's some obvious discussions to have, I think, about sort of future work in sort of either on the Russian mainland or in Russian territorial waters. It occupies a huge proportion of the Arctic. So the fact that you've got active research projects there is, it's great to have that connection already established. The final speaker today is Ilan Kelman, who's based down at University College London and is a thematic leader for the University of the Arctic Natural Hazards Programme. So Ilan, I'll hand over to you if you'd like to share your screen, and the floor is yours.
Okay, thank you very much. I'm really happy to be here, as well as on behalf of the University of the Arctic, where we are trying to take our thematic network to combine hazards and vulnerabilities to think about disasters, what nature is doing, how we are changing nature, but also what people are doing and how people change nature locally and also deal with natural hazards and other natural phenomena. So I'm just going to put my links into the chat, so do feel free to connect in any social media that you use if you want to join the network or to continue discussing these issues, particularly regarding Arctic geophysical coastal changes in the sense of futures. Arctic coastal futures. Where are we going? What are we doing? What should we be doing? And the geophysical changes are many across temporal and spatial scales. So looking at the past does help us consider the possible futures, both in the coming years, decades, but also potentially millennia. So many quick coastal changes happen around the Arctic region. One of the closest analogies for Scotland is the Rega slide, which is one of the biggest underwater landslides that we know of. It happened about 8,000 years ago and significantly changed many of the coastlines and settlements around Scotland and around Norway. Another known rapid coastal change, including the Arctic, is actually tsunamis. So the one in Greenland in June 2017 was potentially one of the largest tsunamis known in, or high tsunamis known in human history. That may have reached up to 100 meters high at source. And we also in Greenland know that forest fires, wildfires are becoming more frequent, which then runoff may lead to changes in coastal ecologies and possibly fairly rapid or possibly slow changes along coasts due to what's happening with regards to these hazards. But there are many other slow changes, which again, we're well aware of. So isostatic uplift, particularly Norway and Scotland, again, gaining a lot of coastal land in some areas, and sea level rise, which Tom mentioned. So we have to be very wary of that, irrespective of isostatic uplift. But then some combine. Erosion processes are both quick and slow. In the Alaskan North and West, some coasts are eroding near settlements several meters per year. And while there's so much rhetoric about climate change migrants and climate refugees, almost all of that rhetoric we see in the media is false. In fact, some of the few people who are almost definitely migrating because of climate change come from Alaska and because of these climate change linked very rapid coastal changes. But some of the Arctic coastal erosion changes are also quite slow. So in Iceland, they're measuring it at maybe centimeters per year, maybe slower, simply from storms and waves. Accretion also occurs. So Mark mentioned one project on volcanoes, and places like Vesmineta Islands in 1973, for example, gained significant coastal land due to volcanic eruption. And other places also combine slow and quick changes, which may flip depending on the circumstances. So apologies for my pronunciation on this, but Aasituk in Nunavut, which we used to know as Grise Fjord, had steady erosion from waves and tides. But then in August 2016, there was a major storm which led to very rapid erosion and actually threatening some of the major community infrastructure there. There are many unknowns. So what happens to Arctic Ocean storms and waves when the ice is much thinner or perhaps there is no ice? And Robin also talked about permafrost degradation. Does that mean that coasts end up being softer with faster erosion, at least locally? Are there other changes? And she also described rivers changing, which in turn again affects the coasts at the output locally and possibly farther afield. So these are the timescales of geophysical changes, but there's people. And so when we look at disasters and natural hazards and vulnerabilities, we're thinking about people. What do these different timescales of changing coastlines mean for human use? Well, for shipping, they're trying to plan the various sea routes, whether it's a Northern Sea Route, Northwest Passage, cross Arctic Ocean, but they have to adjust in real time if there are storms, or again, if there's sudden coastal changes like tsunamis or volcanic eruptions. Same with tourism. While cruise safety has not always been looking far into the future, there are definitely, again, immediate adjustments which have to be made to cruise ships, even as glaciers calve, or again, there may be some of these rapid coastal changes at landing sites. The fossil fuels industry is thinking about infrastructure and investment, sometimes over years, but frequently over decades. So they have to be considering even some isostatic uplift compared to and sea level rise, as well as possible fast events, which may happen in 30 years or in 50 years. But they also deal with immediate issues like the price changes that we've seen when fossil fuel use goes down, and they may have to start up or shut down some of their coastal facilities very rapidly, irrespective of coastal changes. But this really comes down to people and livelihoods. So water, fresh water, is influenced by coastal changes. And this also leads to food, that often in the winter, many indigenous peoples in the Canadian Arctic are used to simply skidooing across the frozen landscape, land, lakes, rivers, and ocean. As it warms because of human-caused climate change, that becomes unsafe, which means that not only the animal patterns are changing and the weather is changing, but they have to change their own behavior to avoid going through the ice in the skidoo, which is basically fatal. So when it comes to settlements, coastal settlements around the Arctic, people have to decide, stay or move as they are in Alaska. Do they change to amphibious settlements or try and live with the changes? Interestingly, settlements like Grise Fjord, which I mentioned, are artificially constructed anyway, that people were forced to live there. So what does it mean if people then forced to move? But all of these human impacts, all of these changes are not happening in isolation. We need to learn from past millennia, but also from others for which the North Sea, including Scotland in particular, is so relevant. Looking at these fast and slow, large and small coastal changes over the past 10,000 years as a parallel for farther north, but also as a parallel for the accelerated changes that we are experiencing now and will continue for at least a century, if not more. So it really is saying, how can we come together as University of the Arctic, as people with interest in Scotland, based in Scotland, looking at Scotland as analogies, and across disciplines, to think about Arctic coastal futures, but also to think about how we can create the futures which we and the coastal peoples would want to have. Thank you.
Thank you, Ellen. That was a fascinating sort of counterpoint to the sort of more process-driven geophysical studies that we heard earlier from Tom and Robin. You know, really sort of engaging the relationship with the geophysical changes with the communities and the people in the Arctic. So that's an important angle that we can sometimes forget about, actually, in a geophysical world, that it actually impacts on real people at the end of the day. So that was great.